be here. And what I want to do today is try to give you a little bit of some brief list of contributions of Professor de Groot. I think I'll need some water. I'll show it pretty fast. Professor de Groot, I have a little picture of him now from the Bangalore volume. It's not, at least the outline is there, right? You can see the smiling face and nothing else, right? Professor de Groot was born in 1931 and he passed away in 1989, obviously very prematurely because of some illness. But during the short period he lived, he did contribute a whole lot to the discipline of Bayesian statistics and also its applications in various areas of, especially in economic theory, and also beyond that in evaluation of forecasters and comparing forecasters, things of that sort. So let me just give you a little short list of his accomplishments here. So he published 3 books which are very popular, used in textbook basically. They were used a whole lot. One of the books was called, what I referred to in my website and description as the Bayesian analysis and uncertain economic theory. It's a very nice book with Richard Sayert, who was collaborating with Professor de Groot on basically applications in economic problem, economic theory. He published more than 100 papers which cover a broad range of topics: Bayesian statistical methods, sequential decision analysis, probability and utility axioms in general, applications in economic theory, information in an experiment, and comparison and evaluation of forecasters. These are some key areas where he did contribute during his short life. He did create one of the very best department of statistics at Carnegie Mellon in a short duration. And also he conceived and did create a journal called Statistical Science. That was his contribution to statistics. Thanks. And that journal, if you don't get it here, you should, because that's something which has.
We get that.
You do? Good. Yeah, it has good collection of basically review articles and expository papers on all kinds of topics in statistics. So that's something very easy to read. You do not need to know much of mathematics to read the journal, basically. And that was his, he spent a lot of time in conceiving the journal and then did work to make it successful. And then now it's obviously fairly popular journal as of now. That's one of his list of contributions. Something more closer to home here. He was one of the two prime motivators for organizing the 1988 Indo-US workshop. Of course, other one you can guess who it was, right? Professor Zellner, right? So obviously that's the other person. And essentially that proceedings volume was published in association with Professor Iyengar, and you have a copy in the library of the volume here. You can have a look, get a good sense of that, basically. We covered a lot of topics in that, a lot of variety of topics in that workshop, and essentially Surekha Rao took over now and to continue the tradition and have continuing workshops, hopefully every year from now on, to make young people interested in this area. Okay, and to me personally, he was a guru in a real sense. Okay, essentially I learned a whole lot from him, both inside and outside the classroom. He was always eager to share his wisdom and also his ideas about everything in life, not just statistics. And his biography is a simple biography published in Stat Sci Journal in 1991 issue. And if you are interested more in reading about it, it's a nice piece to read. Now, I just learned yesterday that Professor Iyengar wrote a paper entitled Bayes Application in Economics, and that's published in Indian Economic Journal, volume 44, page 155, 163. Basically, it's a good reading material for a perspective on the range of Bayesian applications. Basically, he's taking off from the ADA workshop and now he has tried to give you an idea of what is, in general, what are the possibilities with Bayesian methodology in a wide range of applications. And that's a good paper to read. So I'll mention that because he just gave me a copy yesterday, and obviously I read that last night, so I know what is there now. Okay, about these lectures I'm going to cover. I was told that the participants basically, I can assume that they know nothing about decision analysis, okay? So anybody who knows something about decision analysis can leave the room and have fun. You don't have to be here at all. These are very introductory lectures. They represent my interpretation of some of the Professor de Groot's thoughts, words, and writings. This is not very good. I think just about Bayesian decision analysis, including inference. When I say decision analysis, I'll assume inference is part of that, but not worry about it, separately every time. And again, these lectures will not be very comprehensive in any sense at all. It simply will cover some of the things Professor de Groot did, and obviously very selective stuff there. Other lectures in the workshop already provide details on how to apply Bayesian methods to a variety of problems related to decision making. You heard Professor Polasek, Professor Zellner gave an interesting talk yesterday, but basically covers all areas. In fact, after his talk and Professor Surekha Rao's talk, I thought maybe I don't have to say anything at all because everything's covered now, right? So I thought maybe now, well, then that's not true, because essentially for the beginners, I can add something more beyond what they already have said. Okay, so I intend to focus on trying to convince you that thinking and acting within Bayesian framework provides a unified paradigm for the following things. So basically, once you act like a Bayesian, think like a Bayesian, you can do things very in a natural framework, basically. Learning from data and experience. And experience basically will include prior knowledge, historical information, experts' beliefs, everything is part of experience, okay? How do we combine data and experience both with the Bayesian framework? Designing experiments. Forecasting and evaluating models based on forecast performance. Professor Zellner mentioned yesterday that that's very important. Any model you want to use, you want to make sure you evaluate its performance over time. You make forecast, look at empirical data, and see how close the forecasts are to the true values, what you observe in the future. And often models which don't work very well should not be used, should be discarded. Okay, so that's why it's very important to do that. Making decisions under uncertainty. So all these things require, the unified framework requires basically what? It requires that all uncertainties about the observables and unobservables, both the things together, are expressed through probability distribution. That's the key thing. That the data you observe, given the parameters, and the parameters themselves, which are unobservable quantities, we want to express all our uncertainties, all our knowledge, uncertainty part knowledge, as Professor Polasek mentioned just this morning, has to be expressed through probability distributions. Once we do that, then we are in good shape, basically. Okay. Obviously, this task requires hard thinking. I mean, obviously, if you have to think about prior knowledge, try to put all your knowledge and beliefs into a probability distribution may require a lot of hard thinking. But that's not bad, because there's a reward for that. Reward is, I mean, a very, very nice phrase about Louis Pasteur says that chance favors only the prepared mind. So if you're not prepared mind, chance is not going to favor you, basically. So essentially, think about, you pay some price of thinking hard about the underlying problem, the questions you're going to answer, and then you have a framework which is very natural, which is very unified, and you don't have to adapt things like you do for different kind of problems. You do different things in classical framework. That's what you get as a price. So you pay a certain price, but you get a lot more as a unified framework for all these things without worrying about what do I do with this kind of problem anymore. Because like time series, forecasting, everything becomes one framework, and you can work within that. Okay, so that's the reward you get in general by accepting the paradigm that you can express all your uncertainties through probability distributions on observables and unobservables. Okay? So my lectures will cover following. I mean, basically, I'll do a very brief introduction in my lecture one to this morning on Bayesian learning and decision analysis. So a lot of you already have seen that, but I'll just review that quickly and see what my point of view is a little bit different than you have heard already. Then I'll talk about a problem, applied problem, application of Bayesian analysis in economic decision making, just as a sort of a prototype of what you can see happening when you're trying to solve a decision problem. Okay, it's not something very novel, but it gives you an idea of what kind of steps you go through when you're trying to solve a decision problem. Okay. In lecture 2, which will be the day after tomorrow, I'll give a tutorial on Bayesian networks, which is something very nice, current topic these days. What it does is if you have multivariate problem, high dimensional problem, how do we develop some underlying relationships, underlying causalities, underlying correlation structure through a network. So I'll just give a tutorial on that basically day after tomorrow, and then talk about something Professor DeGroote and I have worked together quite a bit on the measuring information and experiment, and how do you choose between experiments. Okay, that's something the last topic will be there, but this will be a tutorial on Bayesian networks. It gives you an idea about how the modern computing apparatus you have can be used to solve complicated problems through expressing your joint probability distribution through a network structure. Okay? So that'll be basically a tutorial kind of thing. Okay. Now, what is the motivation to go Bayes? Before I went to US, I was trained in India, obviously, through my master's program, and never heard the word Bayes over here, right? And essentially, I learned all about regression and design experiments and all the traditional topics you hear about, measure theory also, but nothing about Bayes at all. And I ended up having, as a student at Carnegie Mellon University, which was basically Bayesian Center. And Professor DeGroote tells me, well, have you heard about the word Bayes? No, never heard about that. I know Bayes' theorem, but that's all. It's a probability theorem. Nothing else about using Bayes as a paradigm for making inference and decisions. So he said, fine, but you got to learn about that, because that's the first thing you do when you come to Carnegie Mellon University. I said, all right. We did that, and essentially he's trained me in saying, what are the problems in classical inference? I mean, especially when you're dealing with this frequency paradigm, where you have to sort of think about replicating your experiment infinitely many times, okay? Basically a long-run frequency kind of paradigm. And there are a lot of problems where you can even do that because you do the experiment only one time. When you talk about probability of rain tomorrow, that's something you cannot really replicate a large number of times. It's tomorrow, a specific time, probability of rain. And the interpretation is not anything which is related to long-term frequency. Depending on TV station, they use different interpretation of probability there, but certainly not long-term frequency, okay, essentially. So that's one of the things which I learned about, that long-term frequency interpretation is not applicable to a lot of problems, and therefore you got to learn about other definition of probability which are going very useful in a variety of problems, okay? In a variety of problems. For example, diagnostics. Given certain symptoms, you will say, is the patient suffering from a certain disease or not? That's the diagnostic you want to make, right? And you have data available from in the past patients who have come through the hospital or through the clinic, and both who had disease and not disease, and you have measurements on their symptoms, essentially. Now you want to develop a diagnostic procedure for a new patient who comes in, you measure the symptoms, and now you want to say, what is the probability this person has a disease, all right? That kind of framework does not fit very well in any kind of long-term frequency interpretation at all, because you want to say, this specific person, does he or she have a disease or not? Nothing to do with that. You would replicate this experiment many times, okay? You're not trying to make your inference valid to a population of individuals, only for one individual who comes to a clinic tomorrow, okay? And that kind of situation where you are talking about problems which are very specific to an individual, not to a population, you cannot put them in the framework of classical frequency theory definition. And in this case, obviously, this is not a reasonable thing to do. What you want to do is probably disease given symptoms for this individual, okay? And in general, if you use the frequency theory definition, you're not really doing the right thing at all. In clinical trials, a lot of times the doctors give the p-values, whether or not this new drug is better than the old drug, okay, based on experiment they have done. But they always believe that what they're saying, p-value is not really what it is, but they believe this is probably null hypothesis not being true. Okay, something like that. So that's a wrong interpretation, obviously. But what they believe and what they do is two different things. They do frequency definition basically because FDA tells them to do that. FDA is saying, well, do this if you want your drug to be approved, at least in the past, right? FDA is changing now. FDA in the US has allowed now for the disease, for the development of devices, they are now allowing Bayesian methods already. Not for human beings yet, but for device development, they have allowed the trials, clinical trials, which use Bayesian methods, okay, because they understood the value of that methodology, even though in the context of human beings, they're still a little bit careful about this objective versus subjective inference, because they're afraid that if they allow that for drug development, then what's going to happen is that the drug companies, they have a motivation to tilt inference towards drug approval, obviously, right? So you want to be a bit careful about that. But hope is that in general, over time, we're going to move in the direction of basically more and more Bayesian methods, even for clinical trials and new drug development. Okay, that's what FDA is moving towards over time. It won't happen overnight, though. Also, I mean, he told me, how do you make inference when you have no data available? I mean, you have no data available. How do you make inference? Basically, the kind of problems we're talking about is a given nuclear power plant, is it hazardous or not? I mean, you can't blow it up and measure, how many times it will blow up under certain conditions, because that's all the inference in their situation is based on expert knowledge and beliefs. There is no data available, no real data available. You can't blow up a power plant to find out whether or not it's going to blow up. It just can't happen. So you can't do the experiment there. There's no data available at all. So basically, you're talking about decision making when there is no experiment to be done. There's basically based on expert knowledge and beliefs. Okay, and that's why if you have a paradigm which lets you make inference based on no data or some data, that will be useful than simply trying to do something different for when you have no data available and something else when you have data available. Okay, that's why in this situation you want to make sure that the paradigm you work within does allow you to make decisions under all possible circumstances. All right, and that's where the unification comes in the Bayesian framework, because it allows, first of all, it allows you to combine data and expert beliefs and knowledge, and also it allows you to basically make decisions based on no data also. Okay, so what is the framework we require? Decision making and uncertainty, Bayesian framework. So this is a framework, what is called rational decision making, rational framework. And what you need to do is, first, to solve the problem, first you have to list all possible underlying theories, what we call parameters sometimes, state of nature, or underlying theories for the phenomenon under study. You will make a collection of all possible states of nature. That's what you do, okay? You have to specify that. Yesterday there was a big argument between, discussion about what do we do with data, okay? We had one of the participants here mentioned something about what if none of the theories you list in data explains the measurement you make, right? But obviously if you're making measurements in data, you can include something, all the theories you know about, and an additional one says none of the other theories, but as a possible alternative there, and then you can work within the framework, even though the traditional frequency theory method will not allow you to do that, because if you have models for under each theory and you get something which is not explaining any model, then you have to reject all the models, okay? Essentially, that's not feasible, easily do in frequency theory framework, but here you can do that easily by just adding one extra theta node, which says, but that is something which is none of these above theories, and if my model, my inference leads me to that being the highly probable option, then I'll say, well, I have a theory which is not, I don't know about anything, and that theory, okay? Other thing you need is the list of all possible actions. Options, decisions, depending on what you call it. Actions, options, and in economics you call options available to you, or decisions. You need to start think about what are the possible actions you have in mind. And then the third thing you need is the utility function. You, on the theta across A space, so every possible pair of theta and A is a utility which is our benefit, as was used by Jeffries initially. And basically, economists talk about utility function, statisticians talk about loss functions. They're basically pessimist guys, so that they avoid losses, whereas economists try to make profits. Okay, so essentially, you want to, once you have this collection, you're in business basically. Now, what do you do? We agreed that we make all our knowledge, our ignorance about the theta, which is the true underlying theory, we specify all those through a probability distribution. So analyst does not know which state of nature will occur, okay, or which is true state of nature, but based on his or her experience about the phenomenon under consideration, this is my pencil is phenomena under consideration. Somehow, I think sometimes grease in my hand makes the ink go away, basically. About the phenomenon of consideration, past history and beliefs, assign probabilities or probability distributions on theta. So what you're doing is, you're saying is, here's my collection of all possible theories. I'm going to assign probability to each possible theory that there's a finite collection. If it's an infinite collection, I'm going to specify a probability distribution on this theta space that captures all my ignorance, all my knowledge, all my beliefs about the possible, about these theories being true in the given problem. Okay, so once you specify pi theta, theta, A, U, utility function, and pi theta, you're in business now. You can solve your problem decision making, because, at least for economists, it's not a big deal, because they seem to believe in rational expectations and the expected utility hypothesis. Basically, they want to maximize. So the economic agent chooses the option that maximizes the expected utility, basically. Okay, so minimize expected loss and maximize expected utility, same thing. And therefore, once you have specified the collection theta, the probability distribution pi, action space A, and the utility function U, you just choose A to maximize this quantity. E of the expected utility basically over this distribution, over your belief distribution, for each A, you maximize this quantity over A, and therefore the optimal decision is simply to choose A star, the optimal action, optimal option, or optimal decision, which maximizes this quantity, expected utility over your belief system, over your beliefs on the occurrences of these theories, or what you believe in, or what your degree of uncertainty, whatever you come and call it, the prior distribution. You want to maximize this quantity and choose the A star and maximize that. Once you have done that, well, now you're in business, because this is without any data at all. We have no data at all about this point. We have prior distribution, and we don't collect any data at all. We choose the action A star, or option decision A star, which is going to maximize our expected utility with respect to this prior distribution, and that's our base decision, base action, or base option. That's the optimal rule. Okay. Now, when you have data available to you, what do you do? When your data available to you, so here's the thing: if you're going to conduct some experiment and collect some data, and then make a decision after data is collected. So after the experiment is done, you're going to make the decision. Right? At this point, you have your prior belief specified, but you're not going to make a decision now. You want to collect some more information and then make your decision, basically. Okay. So an experiment is conducted before making the decision, choosing the option. Then the state of knowledge, which is your pi, is now updated to the posterior. So basically, from pi, update the state of knowledge from pi to pi theta given x. And that's what you do by a Bayes theorem. Yesterday you heard in the introduction here how the Bayes theorem works, and I will basically maybe go over that very quickly again. But idea is at any given point in time, you have a state of knowledge about the phenomenon, about these theories, okay? And they are expressed by the starting point, you have no data, you have prior beliefs, but as you collect data, you update every time you get a new observation, you update your state of knowledge through the Bayes theorem. And you make decisions according to the most current belief system you have at that point. Whatever data you have collected, you have updated your pi to pi theta given x through the Bayes theorem, and this is your this is the basically summarization of your beliefs and the data information into the posterior, and this is the tool you use now. Basically, you replace this pi by this quantity pi theta given x, and now choose your, obviously since this posterior depends on the data x you get, therefore the decision you here also depends on the x itself, because the posterior depends on the x, therefore the optimal action you take also changes with the observation x. Okay, that's what you're doing. So essentially, you don't act differently when you have no data, or when your data, basically, you just use the most current state of knowledge you have about the data at that point, and that's the decision-making tool you use all the time. So that's why the paradigm is very unified here, because you just act according to your current state of beliefs or state of knowledge about data, and use that distribution to make optimal decision. Okay, and so it just tells you when you have data coming in, you'll update your prior to the posterior, you get more new observation, and when you get one more observation, basically at that point, the posterior up to this point becomes the prior for the next observation. The next observation, you get a new posterior. So basically, you are continually updating your distribution of data, basically, through the Bayes theorem, and get a new distribution which is based on observed data. Okay, and that's where the unification comes in decision making. Basically, you don't have to worry about which one should I do, but basically use the state of knowledge which is the most current one at this point whenever you make a decision, right? And that's once you remember that, you don't have to remember anything else, because what do I know at this point after I have summarized my knowledge and beliefs and the data into the posterior. That's my current summary, current state of knowledge, and I use that to make my decisions. All right? Is that? So that's the key point here. You make that, then you don't even have to worry about, remembering, is it prior, posterior? It's nothing but prior, posterior simply after the experiment. So the posterior becomes your current state of knowledge, and you use that. Okay? So think about posterior. The tool to be used is current state of knowledge. Current being whatever time point you make a decision, whatever you know about the possibility of this underlying theory, you just use that distribution. Okay, and then you can even forget about the difference in prior and posterior, because what is prior, what is posterior today will become prior tomorrow, basically. Okay, in that time frame, essentially. So if you want to make a decision today, use your most current state of knowledge, which is the posterior after you collected data yesterday. Okay, so think of a timeline, and then basically use the most current state of knowledge as the distribution over your data space or the parameter space, and that's the key summary of your beliefs and the knowledge and the ignorance, whatever you want to call it, about the possibility of these theories being true. Okay? So that's the learning part. You're learning from data. You're learning from data. And this is something you have seen yesterday already. I will go over very quickly. X is observable quantity, conditional on the data being the parameter or the theory, and under each theory you have some distribution about given theta is correct, you have distribution x given theta is px given theta, which is the likelihood function or data distribution. And what you're saying is you'll specify joint state of uncertainty about theta and x both. This is the observable quantity, this is the unobservable quantity. Their joint distribution is specified by the data distribution, conditional on theta, and the prior distribution, which is before you conduct the experiment, what is your state of knowledge about theta. Okay, both these together give joint distribution, and now you use this guy, basically use conditional marginal paradigm. You have this one representation, other representation, pi of theta given x, and m of x is a marginal. Conditional now here, this is conditional, this is a marginal. You can represent in both forms. That is your Bayes theorem says that the posterior now is the likelihood or data distribution times the prior divided by some normalizing constant. Okay, so you have the Bayesian learning simply says that update the state of knowledge from pi theta given x through the Bayes theorem, and then this is what is your at the current summary of your state of knowledge about data. Okay, use that, right? So and if you keep this timeline in mind, basically, then you don't even have to remember prior posterior at all. Simply, you just say what is the current state of knowledge about. So combine data and prior to the Bayes theorem, and once you do that, you use that tool. You just saw yesterday, various forms of representation of posterior distribution. The updating of this is the update part, which is through likelihood function and the prior distribution itself. And once you have done that, but now for tomorrow, this is your prior distribution. You have one more observation to be done tomorrow. This is the prior distribution. Get a new observation. That's the updated posterior. So you can do that sequentially, and that's one thing which is important. That if you're collecting data sequentially, and if you do frequency interpretation of the whole thing, the process is much more complicated, because it depends how you conduct an experiment. The inference might change. But here, since this updating scheme is very simple, if you're doing sequential inference, it's sometimes much easier to get rules in the Bayesian framework. Okay, because your state of knowledge is always represented by, when you make a terminal decision rule, at any point the decision rule will be made basically optimal with respect to that current state of knowledge. Okay, so if the decision is made after observing the x current state of knowledge, which is the uncertainty is replaced, is represented by the posterior distribution. And since the posterior changes with observed x value, the optimal action also changes, because the posterior is a function of x. Therefore, the optimal quantity, optimal rule, which maximizes the expected utility with respect to the posterior, will be a function of x. That's how your data is changing your optimal rule. Again, more data, the optimal rule will change because your posterior is changing. That's the learning part. Okay. Any questions about that? Okay. All right. So, given that in sequential setup, but you have a sequence of observations, independent observations. You have posterior after first I minus observations. This becomes a prior for the next observation, basically. Therefore, the posterior for after the I observation is collected is simply the data distribution by xi and the posterior of the data after the first I minus 1 observations have been collected, basically. Okay, so that's the scheme, and therefore sequential updating and the non-sequential updating basically give you the same posterior. It doesn't really matter whether you sequentially data is collected or insequentially, or in basically one set of I observations, you get the same posterior, basically. So that's why sometimes sequential problems are much easier to handle in the Bayesian framework, because this is your summary of the knowledge from data and the expert beliefs and knowledge and past history. Everything is incorporated in this guide. Okay. Now, that's at any point in time, the optimal terminal action uses the most current state of uncertainty knowledge, and combining information from different experiments is also very easy, because then whenever you have different experiments with different probability distributions, it doesn't matter. Basically, you can have pi xi instead of pxi. Okay, because you now learn a system of updating your of knowledge base about the collection of theories which you're investigating through this mechanism, and therefore, whether you have different experiments or similar experiments, it has the same mechanism to update the state of knowledge. All right? Okay. So the key point is, once the decision maker accepts the notion of expressing all uncertainties in the via probability distribution, that's the key thing, on both observables and unobservables, the optimal decision making process amounts to what Dennis Lindley calls turning the Bayesian handle. Okay, that's what you're doing. Basically, just you turn the Bayesian crank, you have the answer, right? But yeah, accepting the fact that you are willing to do that. You're trying to express all your uncertainties in a joint probability distribution. Okay, and that's where. And once you do that, analysts only need to think about what? The prior, the data distribution, and the utility, the loss function, those three components. Okay, so you spend more time thinking of these important components and then turn the handle, instead of trying to see, I have a type of problem, what do I do in a classical framework? Because all kind of different problems have different kind of structure, therefore they have different procedures available. You have to worry about what procedure do I use for a given type of problem. Whereas here, what you're doing is simply saying, well, I'm going to do that, I'm going to act in this framework, now I think about my prior, what should be, depending on what the collection theory is. The data distribution, this is a component that's obviously there in both the Bayesian classical framework anyway, right? But so what you're saying is, I mean, this is there too. It's hidden basically. And if you use standard procedures, you're still using some kind of standard loss function. You don't specify that. When you say minimum variance and minus estimator, what you're saying is square error loss, even though you don't specify this. Okay. So essentially, these two components are there in the classical framework. This is the extra component, but this extra component really gives you a whole lot more, because now it gives you a unified paradigm to solve all kinds of problems. Okay, rather than trying to work on a piecemeal basis for each type of problem, what do I do in general? Okay, that's what you get in return for behaving or for working in this framework. Okay. I mean, as I just said, in classical inference you need both p, x given theta, and this also. You just assume some kind of standard form, because we just say I'm going to use minimum variance and minus estimator, therefore I'm saying my last function is that, and I'm going to say something optimal in subclass estimator as well. And if I have some other problem, I'd use some other last function but I don't specify. I'm going to use this type of procedure, but that always has in the back of his mind some kind of underlying last function, which is not necessarily explicitly stated in the problem. In testing, you use 0, 1 last function classical inference. So you end up with problem type 1 error, problem type 2 error, two components now. I mean, usually economists understand we have two conflicting quantities. The two types of errors are conflicting because when you're trying to decrease one, other increase. Any procedure you use, try to decrease one, other is going to increase. Okay, so there's a trade-off going to happen. But basically, trade-off is required. And however, the Neyman-Pearson solution was to fix one and at a pre-specified level, assume it's God-given, 0.5, 5% alpha, 0.5%, 0.1%, or 10%, whatever, is not, don't think about where it comes from, and choose a procedure to minimize the other basically. That's the compromise Neyman-Pearson framework makes, is simply fix one, minimize the other, or maximize the utility. And the second component, the problem is two different conflicting objectives. If you try to minimize one probability to this, one of these, other is going to increase automatically. You can't really minimize two simultaneously. In the Bayesian formulation, what you do is don't fix one or the other. What you do is simply say, I'm going to put a prior probability on the two hypotheses, the null and the alternative, and then try to minimize some linear function of these two quantities. Not simply fix one and minimize the other, but minimize some linear function. And that's what you'll see in traditional first course in Bayes. You'll see that once you have prior specified, it's specifying, basically trying to combine these two quantities and choose a procedure to minimize that. So the idea is the following. Let me just give a little indication of that, of what actually is going on there. What goes wrong in the traditional Neyman-Pearson framework? Okay, very quickly. So what you have is, if you choose a procedure, this is your probability of type 1 error. See it's already bad, okay. What I need is there's something here, so. And this is the problem type 2 error. Okay. And what you have is, as you decrease one probability, other is going to increase. Okay. So essentially, if you make this is small, this will be larger. So essentially, you have I think this is 0 or 1, 0, 1. And what happens? This is small, this is large. Basically, the curve is like that. For a given sample size, curve is like that. I mean, you can ignore the data. It's always reject, always accept. That's your rule you can use, but that's the kind of curve you have. And the Neyman-Pearson framework says, I'm going to use alpha, which is small somewhere here, okay? And then simply try to find a procedure which is where this is the best possible procedure, which is in the boundary over here. But what's wrong with this framework is the following. When you increase sample size, this boundary goes lower and lower. Okay? This boundary goes lower and lower as you increase sample size. But if you keep this alpha fixed here, ultimately you can reject any null you want, because essentially because you're keeping alpha fixed. In the Bayesian framework, what you're doing is you're choosing the given the weights in the two hypotheses, you're simply choosing the point which is now this point here. Okay? So then in this case alpha is changing. Okay, and that's why you'll never fall into a trap of this kind, a name and person type, if you use a Bayesian framework, because you're putting your beliefs in the two types of probabilities, two types of errors basically, or two hypotheses, and based on that, your alpha also changes as beta changes, as n changes. Whereas in the name and person framework, alpha is fixed. Usually use something available in table value, which is God forbid that we still people use that 5% value all the time. Okay, but that's not good, because you can make anything. You can reject any hypothesis you want to, because your alpha is fixed. You just take a large enough sample size and automatically reject the hypothesis, because you can find minute differences from the null hypothesis and reject the null hypothesis. Okay, because you have taken a large enough sample size, and that's what goes wrong in the classical framework. But that you will never fall in a trap of that kind if you're going to use the Bayesian framework. We always minimize some linear combination of the two things in general. So what I say here is something which is like don't use automatic pilot statistics. I mean, basically you can't do much. Basically, Professor Zellner talked about using loss functions which are not symmetric at all. Linux loss function, asymmetric loss function, and the traditional classical inference is not geared to solving those problems at all. They use square error loss, symmetric, and in real problems the loss function may be highly asymmetric. Okay, and therefore, if you want to solve the real problem, you think about what the loss function is and solve that problem. Then it's trying to use simple procedure which is optimal for a problem which is not even close to what you want to solve. So a wrong problem, an optimal solution for a wrong problem is not any good. An approximate solution for a correct problem is much better than an optimal solution for a wrong problem. Okay, that's what you're doing when you're using some of the classical procedures based on unbiased and things of that sort. What you're doing is simply you're using loss function which is not correct to your actual application, and therefore the rule you use is not going to be. Somebody can beat you on that using the proper rule. Somebody can beat you in the decision making and its consequences because that person did formulate the correct problem. That's the most key part, is knowing what the question is and answering that question even though approximately. Then trying to answer, use an optimal solution to a question which is not even close to what you wanted to answer to begin with. Okay, that's why. Okay. So inference, it's a Bayesian inference. Basically, what you're saying is you specify procedures for standard loss functions. Okay. So summary information from current state of knowledge. So the 0-1 loss function for estimation, you say mode of the prior if there is no data, of the posterior if there is data. That's the current state of knowledge is. Whatever the current state of knowledge at a given point is, you use the corresponding just mode of the prior and posterior to specify your inference for 0-1 loss function. This is all or nothing kind of situation. The square error loss mean of the prior posterior, absolute error loss mean. These are fairly well known things, and that's why they become like an inference, standard inference for a given problem, because you can just compute those means, medians, modes, and specify them as an inference for whatever loss function you want to use. Testing, you compute the posterior probabilities or prior probabilities of data being the null set or the alternative set, and that's your summary of the posterior basically, which is appropriate for the specified loss function. So basically, when you say action or the decision rule, is simply the summary of the posterior or the prior if there is no data at all, according to your specified loss function. Okay. Now, if your loss function is of this type, basically, if data is bigger than A, you have different slope than if data is less than A. This is loss function, not symmetric at all. Then you don't get the median, you get some kind of quantile. So essentially the quantiles as your inference are some right things to do when you say the loss function is asymmetric. In one direction your slope is much higher in another direction. Then you would not use a median at all, but use some other quantile, depending on how the relative size of these slopes of these two lines. Okay, essentially, so this has become a standard inference thing, because one has solved these for any specified prior distribution for the loss function you have, and now you just specify them as your inference for from the problem. Okay, inference based on the correct state of knowledge, whatever where point you're at, you use that distribution to make this inference. Okay. In the design phase, what do? You choose experiment E to minimize the base risk, which is what you're doing is this is the optimal rule here, D star. Okay, so this quantity here is the expected utility or expected basic at this point expected loss basically for the optimal rule, but this is for a given x now. As you change x, this is changing, the value you obtained is changing. Okay, so you're taking so because you want to choose a design now, you don't have an x yet. What you're doing is you want to say what experiment should I choose now. That means what you say is if I do the experiment E, I may get possible value of x's. For each x, I'll make this decision over here. This is the corresponding loss I'll get for that x. Now I have to average that loss over all possible values of x's. Okay, so this averaging is being done because I have not done the experiment yet. I'm just simply conceiving a possibility of doing experiment, and then if I do the experiment, I get an x value for that. This is loss I'm going to have, and therefore this is the average loss with respect to the. If you do the experiment, what are the possible values of x you will get, and therefore what's the expected loss when you make the optimal decision for any given x. Okay, and you compare these quantities across different experiments, and there's a term for this called pre-posterior analysis. Without doing the experiment, you say, if I do the experiment, I'll get an x value. For a given x value, this is my optimal rule. So this is my loss I'll suffer. Okay, and therefore, I'm looking at an average loss over all possible x's I could get. And now, I'll choose the experiment for which this is minimum. So I compare this quantity for different experiments, and I choose experiment, a design for which this is minimum. Okay, that's where, again, you don't have to really do anything extraordinary. Simply, this becomes your, this is the tool you're using here. The state of knowledge will be this. If you get the data x, and therefore update pi to pi theta given x, this is the loss this is what you will pay as a consequence, and therefore you want to simply average this quantity over all possible x's to decide, choose between experiment E and experiment F. Okay, so you can do this analysis before you do the experiment. You can do this analysis to decide which experiment to choose. Once you've chosen an experiment, then obviously you do. Once your experiment done, you go ahead and do the experiment, get your data, get the relevant posterior, and use that to make your inferences. Now, one thing we do in in math stat courses, I have the same kind of situation I'm in basically. When you teach a math stat course, you simply tell people how to analyze data once you have it. You never think about how did this data come by? Should I even do the experiment at all or not? I'm going to do the experiment. That means I expect to learn something about my unknown parameter from the experiment. But there's a cost to be paid for that. Statisticians simply ignore the cost completely. They assume, here's an experiment, I need to know how to analyze it. But before you reach that step, you have to decide, should I do the experiment at all or not? Because each experiment has a cost to be paid for. And the cost, when you do the experiment, that will give you more information about the parameter. Is the information worth it or not? That part we never discuss in a traditional math stat course. Because we always start with, here's my data, here's my model, what is the sufficient statistic, well, no, that kind of thing. But we never talk about the first step, which is, should this experiment be done or not? And that you can do only, within a Bayesian framework. You can talk about, here's the cost involved for experiment. If I take 10 observations, what's the cost? If I take 20 observations, what's the cost? How much will I learn from those observations? That means basically how much uncertainty will I reduce in my posterior once I get the data, okay? And then I can decide whether or not I should do the experiment at all. Because if it turns out that the cost is prohibitively large and your reduction uncertainty in the prior will not be too much, then you decide, well, it's not worth spending your money to decrease uncertainty because it's not, the trade-off is not worthwhile. But we never learned that in a traditional math stat course at all. We should, because somehow we believe somebody will come to us with the data. Here, please analyze my data for me, right? But that's too late. That's too late. You got to go the step before that, before the experiment is done. Is it a proper experiment or not? Is it going to answer the questions you want to answer or not? Those things are very important, and those we never discuss in the math stat course at all. We should, okay? Now, so that's the pre-posterior analysis thing. Forecasting. But forecasting is fairly easy to do too, because essentially, I've heard from several people already, forecasting involves to forecast a future observation from some distribution which involves data. That's all, right? I mean, it doesn't have the same distribution at all. It doesn't have data X and Y could have different distributions, but they all involve same parameter data. That's how the key linkage between them is they involve same state of nature, okay, same uncertainty basically, same unknown parameter, and therefore you want to forecast Y even though observe X's. But both of their distributions involve data, right? So essentially, what you do is, what you have is theta, Y, and X, those three things, Y, X, and theta. You can write the joint distribution of Y, X, theta. Given theta, Y, X are conditionally independent. We assume that because this is future observation. And if theta is known to be true, then Y and X will have no dependence at all. They are conditionally independent. Therefore, once you can have joint distribution, now you're really interested in Y. And X is given to you. Theta is something new parameter now. Okay, so integrate it out. Integrate the theta out. What do you get is distribution of Y given theta. Posterior of theta given X. Integrate theta out. That's what is called the predictive distribution of Y given X. So again, in the Bayesian framework, any set of variables in which you are not interested, you simply integrate them out. Okay, you have from joint distribution, you have marginal distribution of a subset of parameters, a subset of variables basically. Everything is variable now. X's and theta are variables. What you have is a joint distribution of subset of variables. You work with that. You integrate things, integrate things which are in which you are not interested at all. Okay, and therefore you get this what is called the predictive distribution of Y given X, and use this quantity now. If you want to have a loss function, you want basically want to minimize this loss function. Use the Y hat as a forecast for Y for future observation given the loss function. This is the quantity you're looking at. Your current state of knowledge about Y, because you just ignore theta out, integrate theta out now, and you minimize this quantity to in this loss function, minimize that, and get the optimal forecast. So essentially, same paradigm. Basically, two things. One is the most current state of knowledge, and integrate things out which you don't care about. In this case, you don't care about theta at all. You want only forecast Y. Well, Y, X, and theta are the three set of variables now. Integrate theta out, and now you're in business solving problems for the future, the forecast for the Y. Okay, and this Y doesn't have to be from the same model. It could be a different model. Basically, as long as that model involves theta, that's all you really care about, because theta links the two sets of observations, and the X's and the Y's are linked through theta basically. The theories under which you get distribution of Y and distribution of X, and therefore you link them out and then integrate theta out, get your predictive distribution. Use that. Okay, and then go through the traditional machinery. So essentially, forecasting, designing, inference, decision making, all under just very well specified frameworks, as long as you're willing to think about the utilities and the priors. Okay, if you don't want to think about it, priors, well, there are a lot of tools available which will give you a class of priors which are reasonable for problems. And Professor Zellner will talk about his lecture about how does one develop priors without much thinking, right? Without much thinking. Basically, they are the priors are reasonable for a certain class of problems. Use them, and you'll get inference which is reasonable, and not worry about. If you want to spend more time on that, you think about informative priors and use them if you have time and you're willing to expend the effort to assess those prior distributions. Okay, but the paradigm is very well specified.